Okay, so let's go on. We're going to look today at the connecting electric field to potential. So we're looking at the field, finding the electric field from potential, 29.3. So we've already seen that if you can find the potential of a charge distribution or even a point charge, but we can reverse that and find the field from potential also. So that's what we want to do. So we can find the potential of point charges and charge distributions. So we can also find the electric field from knowing the potential. So we know that we saw that our potential delta V is equal to delta U over Q, where this is a source charge. So it's the delta U over source charges plus Q, where Q will be your test charge in this case. And we know that delta U is equal to minus W. So we can say delta V is equal to minus W, and W is equal to E dx. So W is equal to E delta X. In your book, you use delta S. So we divide that by Q, and there's a negative sign there. So W is equal to E delta S. So delta V is just equal to that. So W, the work, W is equal to Q E delta S. Okay, so if you just put that on top there, then delta V is minus E delta S. Therefore, E is equal to minus delta V over delta S, where E is the electric field. So we can say that E is equal to minus the gradient. So this is the gradient. So you will see that in some places they call it a gradient operator. Basically, it's just the derivative, a partial derivative with respect to x, y, and z. So we can say that in x dimension, the electric field in the x direction is just equal to minus dv dx equal to minus dv dx, and then you can say in the y direction it will be dy dx. For y direction, d subscript y is minus dv to y, and then for z direction, d subscript z is minus dv dz. So we can say that in three-dimensional space, so in 3 dimensions, E, if E has a component x, y, z, then we can say this is equal to Ex I hat plus E y j hat plus E z k hat, if we want to use that notation. So we can say that the electric field in 3 dimensions is going to be the component, which is the partial derivative with respect to x of E, not EV, sorry, minus, not plus, minus, partial with respect to y, v, j hat, partial with respect to z, v, k hat. So the electric field can be written as, if you like, we can put a minus sign out there. So this notation is another common notation. Typically, it uses the gradient operator. It's an inverted delta. So we can use this in an example next. We'll see how it's pretty straightforward. If you know the potential, then you can easily calculate the electric field of any distribution, which makes it simple. So instead of what we did with Coulomb's law or Gauss's law to calculate the electric field, if we already know field, we can if we already know potential, we just calculate field. And we already saw that it's easy to use potential rather than Coulomb's law to do the electric field. Okay, so using the potential is an easy way to calculate the electric field if you use this operator. So you're going to find the electric field on the axis of a uniformly charged ring of total charge Q. So we can say the charge density is lambda, which is equal to Q over L, where L is the length of the ring, which we said is just a circumference. So the way this works is the solution. So we know the potential of a ring of charge to be V ring is equal to Q over 4 pi epsilon naught, and there was a square root of Z squared plus R squared, where we know that R is the radius of the ring and Z is the axis along which we are finding this result. So if you recall, we had a ring like that, and so on this ring, this is Z, and we found a potential at some point on the ring that way. So this is the square root of Z squared plus R squared, where this is R. So we found a potential at that point. So when we do the derivative of the potential, that will give us the electric field at that point. So we are finding the potential at this point. Or that is the potential at that point of the ring, sorry. So E, so we can use E equals minus the, let's say dV dz, since we are interested in taking the derivative along Z. Okay, so we take the derivative over the ring along the Z-axis. So try this calculation and tell me what you get. Take the derivative of the potential that I've given you with respect to Z. Okay, so hopefully you've already completed this derivative. So yeah, E should be given by dz, and then you are taking the derivative of Q over 4 pi epsilon naught square root of Z squared plus R squared. Okay, so you should be able to take this derivative, I hope. So we can bring the Q out, and then you take the derivative, I guess d dz, if you like. So let's actually bring this up here. So what we can do is to take this derivative, you might want to go like this: Z squared plus R squared raised to negative half. So once you set it up like that, you're taking the derivative 2z. So you're going to have 2z and then minus half plus 1, which is going to be equal to half. No, minus half minus 1, certainly. So it's going to be equal to minus q over 4 pi epsilon naught. And then you're going to have 2z, and then you have z squared plus r squared minus 3 over 2, something like that. So this is what you should end up with, something like this. Is everybody getting that? The negatives cancel out. You can remove one of these z 2's, and then you should have q z over 4 pi epsilon naught. Then you bring, actually, let's do it this way. Then you're going to have z squared plus r squared 3 over 2. Okay, so this is the electric field that we would have found when we did this calculation some time back. Okay, the electric field of a ring at some point Z along the axis. You see that it's pretty straightforward if you use the potential. And then finding the potential is easier than finding the electric field at some point in space. So if you just find the electric field, if you just use the potential to find, if you just find the potential at some point in space, then you can just take the derivative to get the electric field. Because with the potential, you don't really have to do a lot of vectors. You just calculate the potential, just like you don't have to do the vectors with the different components, right? So it's pretty easier that way. You find the potential, but then you take the derivative to get E. So this is the electric field along the axis for Z, the electric field along the Z axis, all right? Questions, comments? So let's go on and look at the geometry of potential and field. So we've already talked about the relationship between the fields. So let's consider the point charge with field lines shown below. So if I have a point charge, let's say this is Q, I know the field lines are going to be going radially away from the point charge. So we've seen something like this before, and then we can put one that way. So if I want to draw the potential lines, then I know the potential lines are all perpendicular to the field lines, so it will be easy for me now to draw the equipotential lines for this point charge. I haven't done a good job making it very circular, but these are the field lines E, and this here is the equipotential line V. So the lines are all different, so V is equipotential. So we can say that the potential, is maximum at some point here and decreases as you go away, or depending upon how you want to describe it. But those potentials are all different. Let's say this is potential 3. So this is V3. So this is a potential of line 3. And then there's potential V2. So this will be V2. Okay, so delta V will be equal to V3 minus V2. So the potential difference between the two equipotential lines, V3 and V2, is delta V. So if you move a charge from V2 to V3, there's a potential difference. If a charge moves along V2 or along V3, there is no difference in potential. So let's look at this generically with some other, we'll get some lines. So let me continue. So we can say that the equipotential lines are perpendicular to the field lines. Equipotential lines are perpendicular to field lines. We can say that when a test charge is moved from one equipotential to the other, so when the test charge is moved from one equipotential to the other, there is a potential difference. If a test charge moves along an equipotential line, there is no change in potential, or there is no potential difference. So along an equipotential line, the change is 0. Okay, so the change in potential is 0. So this gives us an idea on how to arrive at something called Kirchhoff's loop law. So this leads us to a loop rule. Okay, so the loop rule is called Kirchhoff's loop law, and we shall see that next. So let's look at that. So let's consider the potential lines below. So we can say that, let's say we have one potential line this way, another one that way, and one that way. So these are some arbitrary potential lines. So we can say this is 20 volts, that is 30 volts, and 40 volts. So let's say that we move a charge from one point to the other. So let's say we move some charge. This is position 1. We move it to position 2. Actually, we can, instead of numbering too many, move that. Say this is 1. So the charge moves this way to this position. Let's say this is D. And then from here it moves to another position, number 2. And then we can move the charge a different way. So this is so moving from 1 to D to 2, we have the following. So moving from 1 to D to 2, delta V is equal to, so we have 1, so it's going to be 20 volts. Actually, let me do it this way. So delta V from 1 to 2 is equal to 20 volts. Delta V from D to 2 is equal to 0. So delta V 1 to D to 2 is equal to 20 volts. Yeah. So when it moves from 1 to D to 2, we just have 20 volts. So we are saying that there's a potential change of 20 volts, and then we can go the other way. So let's go from from 2 to 1 through a different path. So I'm going to draw these things again. So we are now at 2. So you can go from 2 to this point. If you like, you can go down that way, and then go this way, and then back. This is point 1. Okay, so this is still 20 volts, 30 volts, 40 volts. Okay, so 2, let's say this is C, this is B, and that is A. This point is 1. So what we can say is that going from delta V from 2 to C is equal to minus 10 volts. Delta V from C to B is equal to 0. Delta V from B to A is equal to minus 10 volts. And delta V from A to 1 is equal to 0. So the change in potential going from, if you like, delta V going from 2 to C to B to A and to 1 is equal to minus 20 volts. Okay, so what this means is that if we combine the whole thing, so combining the two parts, we have a loop below. So we have something like that. So 20 volts, 30 volts, 40 volts, and we had one goes here to B, and then to 2, and then 2 goes to C, to B, let me see, C to B to A, and then to 1. Okay, so we had a path like that. Okay, so if you look at that path now, what that means is that the potential going from 1 to 2 is positive 20, going from 2 to C to B to A to 1 is negative 20. So the potential difference over the entire loop is equal to 0. So delta V in going from 1 to D to 2 and back to 1 is equal to 20 volts minus 20 volts, which is equal to 0. So this is called Kirchhoff's loop rule. Loop rule or loop law, however you want to think about it. So it just tells us that the potential difference in a closed loop is equal to 0. So delta V is equal to the sum across all the elements of the loop. So that's basically what this is. And we will use this when we get to circuits. We will use this quite a bit. So we will look at each element in the circuit. If it's a potential, if it's a resistor, a capacitor, whatever it is, we look at every element in the circuit. We can calculate the potential drop across that element. So that's the loop rule. So let's leave it at that and go on to 29.4, which is the conductors in electrostatic equilibrium. So if you have a conductor and you put excess charge on it, basically for a conductor, since charges are allowed to move, all the charge is spread on the surface of the conductor. Okay, so we shall see how that works out. So we'll say that, note that, so the charges will all spread over the surface of the conductor. And I've already explained that this is because conductors allow charge to move easily. So suppose we have a conductor below, so we can consider a conducting sphere of charge Q. So if you have a sphere, let's say we charge this sphere to a total charge Q with positive charges. The positive charges will just spread out on the surface of the conductor like that. And so if you look at the electric field on the conductor, it goes out, of course, that way. So what we have is something like that. And so the electric field inside the conductor should be 0 because there are no field lines in the conductor. So the electric field in the conductor is equal to 0. It's at the same potential. So if the inside is all at the same potential, then any change in potential over the inside is equal to 0. So E is 0 inside. The surface is just an equi-potential. So I think that is all. We've already said that I'll say the surface is an equi-potential. So just as we've been doing it, if you think of the potential on the surface, it will just look like that. And so you can draw another equi-potential line like that. It will all look the same. So the surface has equi-potential lines. The electric field inside of the sphere is equal to 0 because the whole thing is at the same potential. So if we have a conductor with a sharp point where we are saying that there are charges on the surface of the conductor, then the field will be highest at the sharp point. Okay, so for example, if we drew something which was like this, it had a point over there. So what we can say is these are all potential lines, these are all charges. So there's going to be a density of charges at the surface which will be higher than at other places. So you will see that the field lines are going to be longer here, like that. So the field is going to be strongest at the point there. So that means that if you draw equi-potential lines, they're going to be much closer together and more densely packed. So we can leave it at that. So the field is strongest at the point. So the charge density and the field is trying to be largest at the sharp corner. Let's go on to the next section, which is capacitance and capacitors 29.5.